Well, good morning. Hopefully, everyone had a great weekend and you're getting ready for a little break here, Thanksgiving holiday, at the end of the week. Um, I hope everyone's doing well after the third exam. In general, the exam went pretty well. I think the average percentage score was about a 91.3, which is an A minus. Many of you, of course, got A's, and some folks didn't do as well. But the bottom line is the course the exam average is about on par with just about what I expected, maybe even a little bit higher. Um, so that was really good to see. And then I was going to make the statement here, given that we've sort of suspended the in-person classes and whatnot. You'll see the rest of the lectures, including the exam review for the fourth exam, appear between now and Wednesday. I'll record the rest of the lectures so everything is available at a flexible schedule. We won't meet in person, or synchronously, rather, I should say. This Wednesday or the following week, everything will be posted. All the lectures will be done and posted, probably definitely for Wednesday, probably for tomorrow lunchtime, uh, and the exam review will be there. I will send out communications with this, but I'll, of course, post the exam review so everyone can watch it at their leisure, even take it at their leisure. In fact, that's totally fine by me. I'm going to open the window up in which you can take it by a bit longer, so there's more time, so no one has to be concerned with that. Um, but I'll make myself available in person to be to answer questions during exam review. So sorry, we're all have this tumultuous schedule with classes being moved. We were already online, so it doesn't affect too much. But I just want to create as much flexibility in case you're leaving campus or anything else like that. And sorry for this all this stuff that's going on. So I'm going to get moving here. Today we're gonna get back to talking about fossil fuels. If you remember the actual last lecture where we presented material, was talking about energy use in the United States, and now we're going to talk about the nuances of some of those fuels that we actually use. So fossil fuels. I want to make sure you understand this is a big issue regarding climate change, regarding energy generation, regarding geopolitics. I want to make sure we understand where it comes from, how do you use it, and what are the environmental impacts of that use. And the key thing I want to mention to you is that we might see electric cars, we might hear about solar electricity, but the bottom line is coal itself, as one of the main fossil fuels, still accounts for more than 30% of the energy in the United States, the energy consumption in the United States. In fact, today, I think it's even fair to say, if you're driving an electric car, most people who drive electric cars even are using cars powered by electricity coming from coal-fired power plants. So it's still a major source. Its only decrease has really come in light of very cheap natural gas that could offset some of the prices. And the key aspect we're going to stress at the table for is coal. Geologically, comes from the result of incomplete degradation of ancient organic matter, or fossilized organic matter. Typically, coal is fossilized organic matter that gets heated up with high pressure and modest temperature and gets converted to a solid rock. So in general, most of the material that actually makes coal, it's actually plant life in ancient freshwaters, swamps, or marginal coastal areas. So estuaries, coastal lagoons, coastal plains, really shallow deltas. They get buried quickly and deeply. These are the areas where you typically find coal being deposited in the geological record. But we tend to think about it as ancient swamps. But anything on continents or near the very narrow margins of continents that eventually get buried quickly has potential to be a source from coal. One of the key differences here, though, is it often has a lot of woody plant material in it. So you typically don't see it in deep ocean settings at all. Just like all fossil fuels, in essence, some organic substrate that's sequestered carbon dioxide from the atmosphere by solar activity grows and dies, in oxygen poor waters, and then basically starts to accumulate in organic rich sediments. Under these conditions, the coal can be partially degraded and often form a thick layer of peat. If you go to the peat bogs if you've heard of the peat bogs of places like Ireland, these are going to be really massively thick, organic rich sediments, often with a lot of fossils, woody material, other plant life, and organic matter. It's sort of think of it as a very organic soup with a lot of solids in there. And basically, if this only gets heated up enough with the weight of the sediments on top of it, you're degraded by the microbes that take out the easy to remove organic matter. you'll see peat formed. Now, in many parts of the world, peat's actually burned for energy. In most cases, the best, most energy-rich sources are actually using areas are using um, peat that's been buried more deeply, more deeply, more deeply, and converted to things like lignite, subbituminous, bituminous, andesite coal. So that this graph, if you notice, there's a progressive smaller amount of material. That's because it's both getting compressed and it's also getting oxidized by microbes and removed. That smaller amount of material um, and is more deeply buried and converted to higher carbon percentage materials. Um, so the peat layer can be inundated by sea level rise, sinking the land, more sediments getting pushed on top of it. That's what causes this to get buried and heated up to higher temperatures. And as those temperatures keep getting buried on top of it, um, again, the volatiles, the gases are squeezed out of the peat. Percentage of carbon increases, the percentage of the actual material sediments decrease, and it actually sort of in this transition from peat to lignite goes from being a sediment to an actual rock. Um, and eventually we sort of call it coal by the time it hits the bituminous the subbituminous bituminous andesite coal. You look at areas like Ohio, almost all of Ohio is in the bituminous to subbituminous range of coal. You can go not very far east of here, and you can find subbituminous coal outcrops as you're driving out of the state. Andesite coal fields are actually closer to where I grew up from in eastern Pennsylvania, but that comes down all the way to Kentucky, along the Appalachian structural front right up against the beginning of the Appalachians as you're coming in from the coastlines. And basically that area was buried much more deeper in the rock record. You almost think of it, it's all at the surface now, and actually that area is above, topographic above Ohio. But in the olden days, if you will, back to about 270 million years ago, that was actually buried much more deeply under this, and it's actually just rebounded with time, where Ohio hasn't rebounded to the same extent. Putting this in a depositional environment, the sort of swamp you would think about near the coast, might accumulate these peat type materials, might be massively thick components of it, but it's really only the components that get buried under more pressure and offshore, where you actually see different types of coal being formed. If this material isn't lithified into the rock record, if it doesn't get buried enough to actually make a coal, it'll eventually be oxidized, eroded, and removed away. And oftentimes peats, even though we know it forms in a lot of areas, it's actually underrepresented in the rock record and not a major component of the rock record. So you can think of coal of different grades, bituminous, andesite, lignite, being in different areas, but in reality, it's often a transition in a depositional environment to how much more sediments get put on top of it, how deeply it gets buried, and how likely it is to make something like bituminous or andesite coal. The best analogy to what the geology of the coal fields that formed places like the coal fields in Pennsylvania, West Virginia, Ohio, which again are we can like it or not in regards to, or we can we always have evolving away from using coal in many reasons, for many reasons. But the reality is this is one of the main aspects of what actually drove the regional economy and the U.S. economy for a long time in this area. So the best analogy today for this is actually the modern mountain building event that's occurring as India is going north and crashing into Eurasia. And basically what we think about this, going back to early parts of the class, is a continental collision. And in that continental collision, both of the continental margins actually have areas that were accumulating organic rich sediments, peat, and as they crash together, that provides more sediments for burial, more pressure to actually let the rock be lithified to a higher degree of andesite coal. So looking at this another way, this actually just gives you the heat. Typically in the United States or in England, we do this in BTUs. In proper chemical units, it's joules per kilogram. But this just gives you a sense of as you actually move from lignite to subbituminous, bituminous up to andesite, the amount of heat you can get actually increases. But most importantly, with regards to the common use of these things, the amount of moisture decreases, the amount of volatiles decrease, and that, as a result, the amount of actual solidified carbon that can be burned increases. So most of your bituminous coal is burned for power generation, electricity generation, I should say. Subbituminous is actually quite polluting, a lot of soot and smog. when you burn subbituminous coal. So bituminous is more commonly, and anthracite more commonly used for power generation. Steel mills and things like that can be used bituminous. Often they mix in a component of anthracite coal for metallurgy, and many steel mills as well actually burned anthracite. This is much less volumetric. Anthracite is much less volumetric in the rock record. As a result, it's a little bit more challenging to base most industrial activities on it, even though it is a lot more cleaner burning coal. So, so the key aspect here is that that transition to bituminous and anthracite is sort of the highest grade coal, relatively few volatiles, and it's important that the reduction of volatiles actually help reduce the amount of smog and soot that's incorporated into them. What's sort of the opposite though is that as if you think about go back here for a second, you think about this diagram. The same amount of metals and same amount of rock material that's in the peat when it's deposited actually doesn't get lost by volatilization and gets concentrated in the bituminous and anthracite coal. So as a result, the downside for anthracite coal is all the heat content's the best, the volatile content's the best, so you see less NOx and SOx and all the acid rain producing components. That coal actually often has very heavy metal enrichment. So things like the fly ash and the coal combustion residue from anthracite can have its own set of problems. I mentioned a lot about the coal fields in the Appalachian Basin, particularly eastern and southeastern Ohio, western Pennsylvania, as well as the anthracite coal fields here in Pennsylvania, West Virginia, and Kentucky. Actually, I guess maybe they don't extend into Kentucky, maybe just West Virginia and Virginia, actually. But in reality, coal fields have an incredible expanse across the U.S. These are just coal fields that are accessible near the surface, such that they can be mined by either surface mining, removing the mountain and actually mining the coal out, or deep mining, digging a tunnel and going in and getting it. But you notice that there's coal in basically all the different areas. There's a lot of lignite in the coastal areas of Oregon and Washington. And the plains have vast areas of lignite deposits, as well as southern, southeastern United States. People don't recognize that the places like Alabama actually have pretty major coal producers, and as well as much of central Texas. The bituminous fields in the Illinois Basin, in Illinois, Indiana, northwestern Kentucky are actually some of the biggest coal producers in our country these days. They are notorious, as we'll get to in a little while here, for being this sort of medium, high volatility bituminous coal, which is really important because they're some of the chief producers of things like acid rain from sulfate and nitrate rich rocks, as well as that state up north here, Michigan, who has great reservoirs of coal as well. In addition to being actually mined to produce coal that can be burned in a power plant, all of these basins are actually quite prominently used for something called coal bed methane as well, where there's microbes that naturally exist and utilize the coal to make methane. In almost all these cases, that methane is produced to sell for power as well. The U.S. obviously is not by any means the biggest producer of coal. We produce about our reserves about 246 billion tons of coal. Well, that's larger than many parts of the world. Russia, as it's the case with many natural resources, as well as Southeast Asia and India, actually have incredibly large reserves of coal. And that's actually one of the chief questions for the 21st century, is that as populations continue to expand, particularly in this region of the world, more than 1 billion in people in India, 1 billion people in Southeast Asia, and of course, well more than 1 billion in China. Most of that has been done on the backs of providing more coal-fired power plants. I don't believe this is true anymore, but as recently about 5 years ago, a new coal-fired power plant came online in China per day. It gives you a sense of just how much coal demands were being burned, and how much of that was coming from all over the world, Australia, in the region, Russia, as well as actually American coal being shipped over to China because of the demands. Particularly from my own experience, having lived in central Pennsylvania, knowing the coal companies there, particularly important is exports of anthracite coal for metallurgy, which there are ships that leave the Philadelphia Navy Yard every day and go to China to provide anthracite coal to the Chinese markets. So that's a good segue into some of the bigger problems with coal. Um, the biggest factors that control the cost of coal is actually shipping and cleaning. The nice thing about coal, if you want to think about it as an energy source, is you can light a match, you can you can start the coal burning, you can drive a lot of BTUs on demand. The downside is that it's most efficiently burned where it's produced. So basically, where you mine it, historically, where we mined it is where we actually put up steel mills and metal smelters and power plants. And as a result, there's sort of this negative feedback loop, if you will, between a resource, pollution, and other pollution. But on the other hand, there's, from a different perspective, there's often a downstream series of jobs that are available economically, although there's a balance between that and pollution that we have recognized was pretty far away for a long time. But before I go on here, I actually want to say, in regards to the water usage we mentioned earlier, one of the main reasons that water use is so large in coal mining, or sorry, yeah, tied to power generation, is the fact that often water is used to clean it has to be used to clean the coal. It's used in steam generation, but often it's also used in transportation. If you put it on a barge, send it down a river, that doesn't probably have any impact on water. Same for the boats that go to China or other locations. But oftentimes these are actually done in slurries. There's examples from the Navajo Nation in Arizona where the coal is put in a water slurry. The water was pumped out of the ground in an area riddled by drought and abject water poverty. Water is pumped to pump the stuff down a sluice, 300 miles away to be burned for power generation. So you can see where that's uses incredible volume of water for this purpose, because the transportation costs really limit how well it can be used. And often if you have to ship it by trucking, it's the cost becomes prohibitive. So you got today about 2.5 million metric tons moved around the U.S. per day. Most of this is going to power plants and factories, much more power plants these days. For example, because of the cost of transportation, in 1995, Wyoming mined bituminous coal retailed for $13 per ton in Wyoming and $30 in Georgia, where power plants are being used. If you come back to those rates now, partly inflation, the relative numbers are about the same, and the prices are sometimes hard to get. But this price basically can add about a factor of 10 to it, where coal produced you consume near an area that's produced, like anthracite coal in central Pennsylvania, it's about $130 per ton in 2020. The issue that I mentioned, that this sort of negative feedback loop, is often what are called mine mount power plants, mine mouth power plants. And what that basically means is that you put power plants right where it's being generated, remove the transportation issue. But as you can see, if you think back to that map of coal mines in very rural parts of the U.S., that often means where you're going to burn the power, you're not actually where you're going to burn the coal for power, you're not actually using electrons. The result, the big issue is you save a lot of efficiency on transportation and water usage, but it actually means you lose the efficiency in the grid. So the grid itself actually can't transport the electrons efficiently, and a certain component is lost. So, just to give you a sense, if you haven't seen this, I'm hoping many of you have seen the coal mines in your travels, or maybe even living in Eastern Ohio, Pennsylvania, something like that. But this just give you a picture of a mountaintop removal operation. Today, and since about the 1950s and 60s, actually even before that, it was starting. Most of the coal mining was actually done by removing the overburden, as it's called. Overburden is all the biological vegetation and rocks that aren't coal, and actually creating either what's called an open pit or strip mining. Strip mining is most common in the mountains of the Appalachians. Open pit mine is more common in the flat-lying geological aspects of the western United States, your Wyoming area coal fields. And by strip mining, they literally strip away layers and layers and layers, like down to the coal and remove it. You can see these are pretty large operations, and now they've gotten to the scale where they're just called mountaintop removal, where there's a whole mountain that's just going to be taken off in layers to get down to all the coal resources. I actually worked my first job as actually between my sophomore and junior year of college, I was actually working as a coal mine engineer in Pennsylvania. At that time, based on the price, you needed to have a foot of coal per 10 foot of overburden to make it viable. Within about a year and a half of that time, it was 1 foot of coal for 30 foot of overburden. This was largely when the Chinese demand for coal increased, and nowadays the metric is about 100 feet of overburden per foot of coal to make it economic. So as a result, if you can think about multiple stack layers of coal that might have 30 feet of coal, that means today we can remove over 300 feet of mountaintop to get to it. In many places they do. The model here is you remove the mountains, you take the coal out, you take the waste rock back in the valleys, and you create this flat lying area. So the hills and valleys of the Appalachians are sort of flattened out a bit. But as we'll talk about here in a minute, some of the challenges related to that is that coal sludge and water are often stored behind the dams, which can be its own set of issues. So the reason that strip mining or open pit mining, mountaintop removal are used is that it's technologically and economically more advantageous than underground mining. Why might this be the case? Why is it that it's easy to do this? For starters, you don't have the human risk of people going on their mines, being exposed to coal dust, to methane, carbon monoxide, things like that. You don't have potential for mine cave-ins, and also when you actually go in a mine, you drill a tunnel through overburden or through coal, and you often mine the coal, but you have to leave what's called pillars in place so the mine doesn't collapse on top of you. And as a result, you often are leaving pillars of coal. You can only mine about 2/3 of the coal that's underground to leave the rest, keep the rock supported. And as a result, you're by definition not getting all the coal. Another factor is strip mining or open pit mining, mountaintop removal, is that you can basically get all the coal out. But like many things, even though there's technological and economic advantages, there are some pretty serious environmental and ecological impacts to doing open pit removal. Before I move on, just take a moment to look at what we're talking about here in terms of thinking about the vast amount of ecological problems. For starters, there's no more ecology, right? There's not really an environment. It's open pits of rock, which are often sulfur rich or metal rich and create acid mine drainage themselves. You're filling in valleys of creeks and rivers, and you're simply removing habitat. So there's obvious reasons here. So we've already talked about acid mine drainage. That's one of them. One of the other aspects here is that these pits that are often filled with coal debris can fill up with water, can fill up with coal waste water, and those areas can actually have what are called sludge impoundments. So what you'll see here is that on some occasions, the increased pressure by the water and rock in these slurries in these areas, these dams can fail, or the material can actually migrate through old abandoned conventional wells, and the sludge can get out of the mine in a variety of different ways. Sometimes this happens by basically percolating through the water systems in the old abandoned tunnels, and whether in most cases there were previously underground mines in these areas. In other, where they're mined, it can leak out and influence water, river, surface, and groundwater. As we'll talk about here in a moment, the bigger concern can often be, collapses or breaches in this overburden, but the bigger concern can often be breaches or collapses in these dams, which can allow this to fail pretty catastrophically, which we'll talk about here in a second. So we already covered acid mine drainage. It's not really that much better by surface mining. In fact, the rates at which it occurs can be pretty prolific because you're opening up the rock to surface, and as a result, the hydration by water and other things really rapidly. But just to give you some examples here, in 1972, failure of a dam on the Buffalo Creek, West Virginia, killed about 118 people, destroyed 500 homes. You're talking about filling up an entire valley with rock debris and water and coal sludge. When that fails, it's impossible to really consider the scale of it. Some other examples was October 11th, 2000, my birthday. Well, at least it was that year, and every year actually on October 11th. But was recent the Big Sandy River in Kentucky. Over 65 miles of the river downstream was flooded. And then possibly the most famous one in recent time, which is actually the one that brought a lot of attention to the fact that this sludge impoundments wasn't working, occurred in the Kingston, Tennessee coal mine, the coal ash spill, which covered 4.2 million cubic meters of slurry released. So to give you a sense of this, in Kingston, this totally devastated the river, the surrounding valleys, roads, schools, houses, churches. Everything was totally washed out. Um, this was in 2008. Some individuals were killed. I forget the actual number, to be totally honest with you. But most importantly, still today, the toxic metal released of things like chromium, lead, selenium, manganese into the environment in those areas uh, were such that the area will never be inhabitable again. Um, so when you recognize these big impoundments are often not exactly a permanent structure, and usually aren't built well enough to handle changing climate, major flooding, major precipitation events, things like that. You recognize this is something that's repeated itself, and it has repeated itself time and time again. Um, what other alternatives are there? What do you do? You're trying to do, they're trying to do mine reclamation. People have used the material trying to use it for other construction debris, like pulverize it for road aggregate and stuff like that, or construction aggregate. But the reality is most of the material is just disseminated around landfills or put in these retaining ponds. There's just some more photos of that. This is 1 mile from the failed retention pond, as a 25-foot tall wall of ash that washed through this area, wiping out everything in its path and leaving a pollution that it's not even salting the earth. It's literally just poisoning the earth for a long time. Nothing will grow here for numerous generations based on the amount of contamination. This gives you a sense of for a scale. It's actually ash is now multiple feet, up to 20 feet thick of this toxic ash slurry. Of course, the water will move on eventually, but the rock material is not soil and can't really be safely vegetated. Many homes were totally wiped out by this, and as a result, the environmental impacts of coal are pretty profound. What I didn't get into much here was just the impacts of ash debris from the burning process. Here we're just talking about the mines yet, right? The acid mine drainage, the slurries, mine dust, of course, is a great threat to people working on site, but obviously people living in the area are exposed as well. Materials, dust particles can travel pretty extensive distances, in fact. The reality is, as oil becomes more limited, increased coal mining may occur. That idea is true in a sense that oil has become more restricted, but in reality, unconventional drilling, shale gas development has actually brought so much natural gas on it. It in fact itself has suppressed coal mining, and actually has opened up many more opportunities for oil. So I believe the trend in coal being decreased is probably going to be somewhat permanent. The bigger issues we didn't get to yet with coal mining is the fact that when you burn natural gas, you get CO2 and you get water and heat. When you burn coal, you leave behind ash, depending on the type of rock mass. It can be 5 to 20% of the original masses of coal. It means that the coal can be, coal by definition has to be at least 50% carbon, but most of it that's burned is more carbon rich. Something has to be done with this. Fly ash and coal combustion residue are the byproducts. Fly ash is the material that is burned and is captured coming out of the vent stacks. And coal combustion residue is the slag or the heavy stuff that falls down. Both are byproducts of burning finely ground coal-fired power plants. This has been around forever, coal combustion residue. Fly ash is a relatively new component because it's nowadays, back 100 years ago, they used to burn coal the size of golf balls. Then it went to pea size. Then it got to smaller. Now, what we've recognized, you get more energy per mass of rock by pulverizing to smaller and smaller grains. So they actually pulverize this to extremely small grain material, push it into a furnace. I totally lost some blank there. Push into a coal furnace, and as a result, the finely ground powder can be much more easily mobilized or even volatilized to air, not volatilized in the gas sense, but released by suspension in air and its potential hazard. In addition, obviously, coal burning releases huge amounts of CO2, other greenhouse gases. There's no way around that for any of the other fossil fuels, let's be honest. But the thing about coal, so the CO2 is the same for everything. The thing about coal is that other greenhouse gases such as benzene, toluene, and as well as sulfur oxides and stuff like that are released because of the fact they're concentrated in the coal. With many things like natural gas, you can purify those other components out of out of the system, not really allowed to get into the environment. So, what are these coal combustion residues? Why do we care about them so much? They're solid materials that remain after the coal has been burned, generate electricity and steam or steam, usually steam to make electricity. Um, with the fly ash, so the smallest particles that gets mobilized. The coal combustion residue is really bottom ash, bottom slag, and then any materials, flue gas, desulfurization materials. So there's typically on the stacks in the United States now, there's these filtration systems that actually collect material, removing sulfate, sulfite, and various other metals and dust. All that material gets lumped in together. As a result, you're making, in many cases, quite a concoction of pretty nasty things. And what do we do with them? As I mentioned, a lot of them are used to fill in the old abandoned mining areas. A lot of them are used to do valley fill-in areas to sort of level off the mountaintop removal aspects. There are some sort of creative uses, putting in building materials, roads, trying to do something beneficial out of them. But their uses are they're huge, but they're still small in comparison to how much we're generating this every year. One other aspect of coal mines, this is probably more near and dear to my personal experience. They're actually coal mine fires. People don't not tend to recognize this is actually an issue. There's about 1,000 of them burning in the world today. One prominent one was near and dear to my heart. It's actually the town I grew up in. So here's a town, Centralia, Pennsylvania, about 1962. Fire caught was caught a coal seam on fire. The fire burned into the town, and actually, when I was about 7 years old, we had to sort of abandon ship and relocate our house to another area. So if you go there today, it sort of looks like an abandoned apocalyptic remnant, but there's still an active burning coal mine. Mine fire is not as obvious. This is an older picture, but this is a picture from about a year ago. It still steams and still burning, and I take people on field trips there in normal years. But there's areas where the road's cracked open. This is actually totally fake. It was a kid on my field trip, decided to go down and play a prank on everyone. But this is the road I used to drive to school in. It sank down about 15 feet just as the coals burned out beneath it. They kept trying to pave it. The road just kept splitting open. Eventually, we had to abandon the road as well. So, this is just an example. It's a nice little small Appalachian town that remains no more. Just one other example of how coal fire power plants and coal mining can influence the environment. So one of the things we want to talk a little bit more about here in detail is just the aspects of the greenhouse gas emissions from coal. So what we're going to do is consider a typical coal burning power plant, a 500 megawatt coal plant. It's a pretty sizable coal plant that produces about 3.5 billion kilowatt hours of energy per year. That's enough to power a city of about 140,000 people. So that tells you just on the basis of it, right? That means a city like Columbus, in the metropolitan area of Columbus, probably needs about 10 of these power plants, right? Not quite 10 power plants, but something on that order, just to get you some perspective. That burns about 1.43 million tons of coal per year, uses about 2.2 billion gallons of water per year, as well as 146,000 tons of limestone to sort of balance out the acidity and the chemistry of the rock in order to remove the sulfur and whatnot. So, aside from energy, we talked about the CO2 emissions, we talked about the power generation, but how much, what are the other factors it produces? Well, typically, if it burns bituminous coal, that produces about 10,200 tons of nitrogen oxide. That's NOx. It's a major cause of smog and a major cause of acid rain. By necessity, it produces 3.7 million tons of carbon dioxide. And if you're going to burn it for burning a fossil fuel, you're going to produce CO2. 500 tons. And remember, this is per year. 500 tons of small particles. These small particles are often in the size range, if they're released in the plant, that they're a hazard to health. They can be respired into the lungs. They can be respired into the throat and into the mouth. And also on the small side, less than 20 microns can be small enough they can actually respire in the nose and actually transported along the neuronal pathways right to the brain. So there can be a whole series of different issues related to this. And about 220 tons of hydrocarbons that don't burn completely. These are the source of the smog you used to hear about in terms of the, London back in the day, or Pittsburgh, whatnot, that the tons of, relatively small amounts of hydrocarbons can make some pretty large components of smog. 720 tons of carbon monoxide we all know, is a poisonous gas, also a major contributor to global warming from incomplete combustion. Luckily, as long as it's not in a confined space, it is oxidized relatively rapidly to CO2, but still contributes to global warming and removes oxidizing capacity of the atmosphere to remove other things. And then about 125,000 tons of ash and 193,000 tons of sludge from the smokestack scrubber, in addition to the materials we talked about above there. So with that, you have to recognize that it's also in terms of direct release of toxic metals in the area, and this, of course, disproportionately affects people living near those power plants. 225 pounds of arsenic, 115 pounds of lead, 14 pounds of lead, 4 pounds of cadmium, many other toxic metals, often multiple of them at the same time. So I'm painting a bad picture here, but it's an issue that when people make the comparison about just greenhouse gas emissions between methane and coal, I think the whole story needs to be considered. Coal, I think, on average, ends up always being worse for people. And I'm from a coal mining town, not against it. They're wonderful people and whatnot, but it's not exactly the easiest way to make a living. If you look at coal production by region, you can see that this is back to 2001, 2006. You can see that Asia Pacific, that actually includes Australia, which is a major producer of coal, increased rapidly. Most of Africa, Europe and Asia, and even North America has actually seen a steady decline, if you will. Most of the actual internal consumption of coal had been decreasing in our area, and the production didn't decline quite as fast because we were actually exporting coal to places like China and other developing nations. But clearly, most of the consumption today is driven by China, India, and other parts of Southeast Asia, and that they're ramping up their production. And you can take an economic perspective on this. If we can, if it's going to be burned and we can export it as the U.S. can be important for our economy, the reality is the transportation costs limit that. So it's why you see mainly long distance transport of things like anthracite coal, which are high grade, and metallurgic coal for a very specific purpose. So we're going to transition away from coal mining here, and for the rest of the lecture today, we're going to talk about oil and gas. These are hydrocarbons. We kind of call them hydrocarbons. Oil and gas deposits form a similar matter to coal. What happens is you get organic matter, partially decayed, buried in sediments, and over time breaks down to make oil and gas. So different than coal, most of the coal is again produced by plant material. Oil and gas is actually typically sourced by bacteria, algae, and plankton growing in the marine oceans, or even in lakes in some cases. They're sucking down CO2 from the atmosphere just like those plants, and storing that CO2 in organic matter. Typically speaking, these are in lakes or in deep oceans, sourced from bacteria, algae, and plankton. And as a result, many of the oil deposits here offshore, we are often mining them now or extracting them now onshore, but that's because geologists brought them on and created them with the continents. So many of these oil deposits are actually found in what we call marine basins. Ohio happens to be a marine basin inland. Here was shale gas to the east of us, and in Pennsylvania, that was the basin that was inland of the encroaching African continent that led to the Appalachian Mountains. That ocean basin now is rich in oil and natural gas deposits, which we've been extracted in the U.S. and in Ohio or Pennsylvania for a long time. The most abundant of the hydrocarbon liquids is methane, about 80%. This is specifically natural gas is the most abundant. 80% of which is methane, and smaller amounts of ethane, butane, propane, and hydrogen. You probably interact with natural gas in more ways than you think you do. Propane, obviously, we think about home heating and propane tanks for grills and stuff like that. Butane, if you're a smoker, you having your lighter. Ethane itself has now become far more important for the global economy because historically, many of the byproducts of the petroleum industry have been refining oil down, getting constituent components for gasoline, other components, but then using these to distill or refine specific chemicals that could be used for feedstocks for other industries. Nowadays, this is very important to Ohio, Pennsylvania, and Virginia. Nowadays, most of the field has changed. We're actually focused on ethane cracker plants, we're actually, rather than taking this big complex mixture of fluids that makes up oil and refining it down to extract the components you want, instead now there's a move towards using ethane, cracking the ethane in controlled conditions, and actually generating plastics and things like that. So there's something in our region here in Ohio called this Tri-States Energy Partnership. Involves West Virginia, Pennsylvania, and Ohio. And there's 3 ethane cracker plants being built with the idea that they can use the natural gas from our region and move much of the plastics manufacturing back into the United States that's currently, shipped in from China and other parts of the world. So I mentioned it's like oil and gas. Oil and gas is like coal, kind of the same thing here. It gets buried at increasing temperature. Initially, the organic matter looks an awful lot like lignite. As it gets buried deeper and deeper, it becomes oil, eventually natural gas. But it's the breakdown of those organic components, and I won't bore you with it again. Broadly speaking, I won't go into this much detail, but those organic rich source rocks, what's changed most of the oil and gas industry, I should say, is those organic rich source rocks. Most of the oil and gas that was extracted for a long time, it's formed in those source rocks, migrated up to some sort of trap. People will drill down to those areas. A trap is a three-dimensional volume of in a rock, where it's usually a high porosity, high permeability formation like sandstone or limestone. Oil migrates in, and there's some sort of cap rock that's maybe we would think of as an aquitard, perhaps, with low amounts of porosity and permeability. The oil accumulates, and you drill a well down, and you tap that reserve. Of course, in the aspects of shale gas that are more akin to what's been going on in the last 15, 20 years, it's typically that we're actually going down to the source rock and drilling a well inside of that to extract oil and gas. But key thing here is that oil can be generated as it's buried and heated up. It can be produce oil and gas over hundreds of millions of years and be accumulate in various formations that are tapped today. I won't go into the geology of this too much. I just don't think we have enough time to go after it. There are petroleum geology classes on campus that are relevant if you wanted to move forward with learning more about this. But basically, most of what you should know about petroleum systems is something called smarts. You can understand the source of the oil or gas, how it migrates, how much porosity and permeability there is, where a aquitard, which in the petroleum world is called seals, are going to be that won't allow the fluids to migrate anymore, recognizing they're buoyant, want to migrate up to the surface. Then you can basically find three-dimensional trapping structures. It can be something like this, which is called an anticline, or it could be rock formations that are basically just low porosity abutting each other, and that creates a reservoir of oil that can be tapped in the conventional world. If we're doing non-conventional, we just can come down and drill a well in here and try to get the oil or gas out of the formation itself. So in all cases, this industry has actually only grown in the last 15 years. Oil and gas has probably gone a bit more towards natural gas than it was before, just like the decrease in oil. Well, there's a lot more focus on getting natural gas because it can be burned cleanly, transported efficiently. But the macroscopic trends are that that's actually, again, increasing. There's been a shuffle in which fossil fuels are being used towards natural gas from shales. There's been a shuffle towards which renewable energy resources are being used, away from hydroelectric towards solar and wind. But the actual percentages haven't changed very much. There's a lot of optimism it will soon, but notably that hasn't changed just yet. So there's some language around oil and gas recovery that I think people should be aware of. The first thing here is called primary recovery. Now, the primary recovery is using natural gas reservoir to extract oil from the subsurface. Typically, in that situation, you can get about a quarter of the oil in a reservoir out by drilling a well. This is an example of a very typical conventional well. This would be a vertical well drilled down into one of these sort of trapping structures. Okay, and what that do is this is basically called a nodding donkey. There'll often be a motor on this. Okay, and that motor will run typically off of the natural gas that comes up out of that well. So this motor will actually have a pipe that comes off here, comes back somewhere here, powers the engine. As a result, this thing can run itself. And what that does is just sits there and pumps and pumps and pumps and produces about 25% of the oil, that's available in that reservoir, which means implicitly that 75% of the oil doesn't really make it out. Okay. So if this TV reference is probably too old for all of you, but if you ever heard of the Beverly Hillbillies who shot a gun after trying to shoot a rabbit and hit a patch of oil and created a gusher, or you've heard about oil gushers in Texas and whatnot, the punchline with the oil industry, broadly speaking, is those days are pretty long gone. You can think about the oil resource in the subsurface as a pyramid. Okay, the closer you are to the top of that pyramid, there's a this is a pyramid you actually want to be towards the bottom of. The very top of that pyramid is actually a very small volume of oil and gas. It's very close to the surface. So typically back in the olden days, people could go around in the farm fields and find oil and gas seeps. They could find surface slicks where oil or gas were emanating out, maybe salt springs. People would drill wells there, and they'd produce gas and oil or gas, I should say, for or both for a extended period of time, and that was sort of the natural pressures of the system that were out of whack and allowed oil and gas to be recovered. Most of the oil and gas that can be produced by that all over the world is now entirely gone. If it's that easily exploited, somebody's done it. And today, what you find instead is that almost all the reservoirs need to actually be sort of pumped in some form or another. Typically, for many of you have seen these nodding donks, this thing will go up and down and creates a pressure that lifts the oil or gas, but typically oil out of the reservoir. But that actually only allows you to recover maybe 25% to a third of the oil in a given reservoir. And what's actually happened throughout the evolution of oil and gas in the United States is that most of the oil that can be produced in that manner by simply pumping is now just with the same way as the top part of that pyramid. So we've moved down to the next rung, if you will, in that pyramid. The oil that can be produced by pumping is a lot more volumetric than what could be produced spontaneously by just poking a hole and relieving the pressure. The gushers that we talked about in yesteryear. But now the oil industry, right around probably in the United States, the late 80s and in other parts of the world through this time period, the wells that can be easily produced by just putting pumps on the wells and getting that primary productivity are getting fewer and far between. So major oil fields in the United States, areas like Texas, areas like the Illinois Basin, the Appalachian Basin where we live in here, they've produced oil for 150 years. All the gushers have been gone for a long time. As we move down that pyramid, people have gone to these sort of wells that are pumping oil out of maybe 300 feet, 500 feet, 700 feet, something like that. And they can do that by providing pressure. Most of that productivity is actually now gone in many parts of the world. There are areas in the Middle East, Venezuela, and new emerging fields like offshore fields in the Gulf of Mexico and whatnot, where you're still able to go go deeper in that pyramid, where you have to drill a well deeper and produce oil that way. But most of the oil industry in the United States today, or at least prior to unconventional shale gas development, and it's been this way for about 20 to 30 years, has been coming from going out and using some sort of enhanced recovery material. So what you'll do is you'll inject water, you'll inject steam, inject chemicals, often you'll inject CO2, even nitrogen gas. You want to increase the pressure of the system. This is called enhanced recovery or secondary recovery. And the idea is that by doing so, you can actually mobilize more oil and gas out of the reservoir. So often this will increase the recovery rate up to about 50 or 60% of the oil that's in the reservoir to balance out that first 25 to 30% that was produced initially. And as a result, you can often produce as much oil with this steam injection or water flooding or CO2, for example, as you could by initially pumping out of the area. So that scenario often has wells looking very much like this. In fact, it's often the same well producing from the reservoir, but you might have a series of wells surrounding this area that push steam in and try to push the oil towards a target. If you look at the oil industry in the United States, back to even as far as the mid 70s, our oil production has been a pretty rapid decline. Enhanced oil recovery, obviously stabilized it for a while, brought it back up, but it really wasn't until around 2008, 2010, 2012, where the unconventional oil and gas development, which started much earlier than that, but really got kicking around 2005, started to kick in, where the U.S. has now gone from, trying to get every last drop of oil out of these, shallow reservoirs near the top of the pyramid, towards just drilling deeper wells and going after some, some really much more massively volumetric reservoirs, than a lot more oil and gas. So the punchline here is that the U.S. is, we've lost our capacity really to produce primary recovery oil from most shallow conventional wells. We were leading innovators, in fact, in getting enhanced recovery in many of these other areas. There are plenty of areas like the Middle East, North Sea, Venezuela, where oil can still be produced by primary recovery, but that's produced really quickly. I want to give you a perspective on this. As we think about this process, we're thinking about oil, being pumped to the surface, whether it's by primary or enhanced recovery, lifted by pumping or pressure, brought to the surface and burned for energy. All right. So, in perspective, what does that look like? This is before shale gas development. This is where, the majority of the oil was being produced from the Middle East, Africa, particularly Nigeria was a major component of that. Russia has always been stable in oil production. South America came on, and North America was in terms of remaining conventional oil reserves, was really quite profoundly small. But to give you a sense of the scale of this, if you look at a field I studied in the North Sea, where Exxon was working with, in a partnership with BP, they had an operation there that actually employed thousands of people, basically produced billions of barrels of oil. Worked on it for, people worked this field up for their entire careers, 15, 20 years of a team building this. And that entire oil reserve being produced by this sort of primary and secondary recovery or enhanced recovery actually was completely depleted in about 6 days. All right. So just think about the scale of which we're consuming energy now, and how important it is that we move into the deeper parts of the pyramid if we're going to sustain society with fossil oil and gas reserves, or in fact that we build a different pyramid and get unconventional, not just unconventional fossil fuels, but renewable forms of energy. So this graph, in terms of the billions of barrels of oil remaining in reserves produced by conventional drilling, is accurate. What's changed, of course, which we'll get to in the next lecture, is just how much unconventional oil and gas development has put the total oil and gas can be produced on its head. In fact, the U.S., throughout most of my life as a geologist, when I was in school, I was told you're gonna have to, if you go into petroleum geology, go into geoscience, you'll be working all in Africa, and working all in the Middle East, and you'll be working, all these areas. You'll never work in the U.S., and I wasn't opposed to that at all. But the reality is that now, we imported something like 40% of our oil and gas at one point from the Middle East, and like 42% from Canada, with a small percentage from South America. That percentage has actually increased, but there was almost none produced in the U.S. Less than 20% at the point, and now we are a net exporter of both oil and natural gas. So as I might have said before in class, we are building terminals all around the coastlines of the United States to import natural gas to keep the homes heated. And now we have actually re-engineered those terminals to export natural gas from many locations of the U.S. I'm going to end there. Again, this will be the last sort of synchronous lecture. Unfortunately, I don't want to. I'd much prefer talking with you all, and I thank you all that have signed on in person. You don't have to by any means, but it's nice to know there's at least somebody interested in the class. It's believe me, I'm sure many have had little challenges learning this semester. I've certainly had challenges teaching, not seeing your faces and being able to get questions and stuff like that on a regular basis. But this will be our last synchronous lecture. Thanks for hanging in there. Again, all the other lectures we posted, just so everyone has flexibility as people start to scatter with getting home for Thanksgiving and getting off campus and just generally getting to a safe location. But hope everyone does well. Thank you for listening this semester. I'll of course keep talking at you and record myself through next week and the exam review. But thanks for hanging in there, and I'll see you all virtually.